Hello everyone, this is Professor Roman. Welcome to the 7th video in my video lecture series, An Introduction to Discrete Mathematics. We have finished our discussion of sets and one-to-one correspondences, so it's time to move on. And the next item of business is inductive proofs and inductive definitions. Before I begin, I want to talk about a bit of notation which you may be familiar with. There is a very concise and useful notation for sums, known as summation notation. For example, the sum of the first 100 positive integral powers of a variable x would be denoted this way. So it is x to the 1 plus x squared, all the way up to x to the 100 added together. So the way I would read this expression is the sum of x to the I as I ranges from 1 to 100. The Greek letter sigma, it's the uppercase sigma, stands for sum or summation. The letter I is called the index of summation. The starting value for the index is the lower limit, which in this case is just 1. And the final value, the ending value, is the upper limit, which in this case is 100. You can use any letter you want for the index of summation, provided that it's not being used for some other purpose, of course. But the most common choices that I've seen over the years are I, J, K, N, and M. L isn't so common because a typed L kind of looks like a 1, so it's a little dangerous. But I do use a script L myself sometimes. The value that's being, whoops, I don't know if I can do this. The value that's being summed, in this case x to the I, is called the summand. If the upper limit is smaller than the lower limit, then in a sense the sum doesn't make any sense, but it's taken to be 0 by definition. So in this case, sum I goes from 5 to 4, x to the I would be considered to be 0. In general then, this is what the notation looks like. The sum I goes from L, the lower limit, to U, the upper limit, of an arbitrary summand P of I is P of L plus P of L plus 1 and so on up to P of U. Okay. Here are some examples which I'll let you go through. I don't think you'll find any surprises, but let's at least take a look at this one. In this case, the summand 3 does not depend on the index of summation k. No problem. We just add 3 plus 3 plus 3 plus 3 as many times as the range here would indicate. So 5 copies of 3. There is a quite useful technique when dealing with summations written in summation notation that's called index translation, and that's my name. I don't know if anybody else would use that term. It's probably not standard, but it is descriptive. So let's take a look at this sum, for example. You might be annoyed by the fact that the exponent is j plus 1 and not simply just j. We can fix that. If you subtract 1 from the exponent here, you have to make an adjustment, and the adjustment is to add 1 to the range of the index. So you would kick this up to 1 and this up to n plus 1. And it would look like this. So these two are equal, and we have a little tidier summation, sum end. If you want to double check this, if you look at this again, ask yourself the following question: what is the range of values of the sum end? Well, when j is 0, this will be x to the first power. So this summation ranges from x to the first power to x to the nth power, and to x to the n plus first power, and that's exactly what this does as well. Okay, the first exponent will be 1, and the last exponent will be n plus 1. So you can feel free to add an integer to the summand, to the index of summation in the summand, provided you subtract the same amount from the range of the summation. In other words, you subtract 1 from the upper and lower limits. Or you can add a value to the index of summation in the summand, then you have to subtract that value from the upper and lower limits. Okay. This index translation is very useful when you're trying to deal with multiple summations. So I'd like to simplify this expression, but the exponents in this case don't match. Well, I can do index translation on this one. I'm just going to recopy the first sum, but the index translation gives me this. I've subtracted 1 from the exponent, so I add 1 to the limits. Now I have the same summands in both cases. But the limits are not the same. So what I do then is I pull out limits that appear only in one of the two sums. So for example, I equals 0 is in the first sum, but not in the second sum. So I'll pull out that term from the first summation. And of course, x to the 0 is just 1. And then I'll write the rest of the summation. Now it starts at I equals 1. The upper limit hasn't changed. For the second summation, the term I have here that's not in the first summation is the final term, the last term, x to the n plus 1. So I pull that out, oops, and drop the upper limit by 1. And I can gather together these loose terms, and I have then the same summation in both places, so it's twice that. This is worth studying a little bit to make sure you follow the technique here, because it is extremely useful. Summation notation might take a little time to get used to. It can be saving in space and efficiency, but sometimes if the sums are small, you may want to write them out anyway. If you're having trouble with summation notation, I would suggest just give it a little practice. There's some exercises in the book, and it should sort out for you. And just to put it in perspective, let me show you something. This is Einstein's summation notation. So if we have two indexed sequences, now this sequence of the A's is indexed with a superscript. These are not exponents. They're just integers to separate, to distinguish between the different elements. So this is A superscript 1, A superscript 2. You read this A3, not A cubed. Okay? And here's a sequence that's written with the usual subscript indices. if we want to take this sum here, a1b1 plus a2b2 and so on, this is how we would write it. I got a little issue there. This is how we would write it in standard summation notation. This is how Albert would write it. So Albert was pretty clever, and he was able to deal with the upper and lower subscripts, the upper and lower indices. When they're the same, you sum over that index. And somewhere there has to indicate what the limits of summation are. But that's enough about Einstein's summation notation. I will never use it. I used to use it a long time ago, but I stopped using it. So we won't talk about Einstein anymore, except actually I do have one interesting story. It's my favorite story about Einstein. I had a friend and colleague when I was teaching at MIT. We worked together, and he was an undergraduate at Princeton at the same time Einstein was there. And one day he went to attend a lecture by someone, not Einstein, in a huge lecture hall, seating somewhere around 300 people. And he came in early, sat in the front row, facing the blackboard. The room was full, eventually. And before the lecturer came in, of course, people were talking, and it was very noisy. And my friend sat there, looking straight ahead, waiting for the lecturer. And all of a sudden, the room went dead silent. It was not the lecturer. He hadn't come in yet. So my friend turned around to see what was going on. Albert Einstein had walked in the room, and all 300 people stopped talking. So that's my favorite Einstein story. Let's turn now to the main topic of this lecture, this video, and that's mathematical induction. You may know, be familiar with induction already, which is good, but I may say one or two things you haven't thought of before, so I would suggest you bear with me on this. But if you're very comfortable with induction, you can skip the rest of this discussion. Mathematical induction is especially useful for certain types of proofs. It's very specialized, but when it works really well. Let me give you a simple example to start with. Suppose we want to prove that for all positive integers, n is less than 2 to the n. Now, this is a statement that actually represents an infinite number of different inequalities, one for each value of n. So we are trying to come up with a single proof that works for infinitely many situations. We can't do it simply by substituting values for n. If we were only concerned with n ranging from 1 to 10, we could write out the 10 inequalities and say, yes, they all hold. However, suppose we can show two things. First, this inequality holds for the first value n equals 1. And second, if the inequality holds for any particular value of n, it must also hold for the next value, n plus 1. Now, to be clear, this is where some students have points of confusion. We are assuming that the inequality holds for a particular value of n, but only for the purpose of showing that it holds for n plus 1. So it's a temporary assumption. Then we can argue that the inequality holds for all values of n. And the reason is the following. If the inequality failed to hold for some particular value of n, there would be a smallest value of n for which it failed. I call that n naught here. But n naught is not equal to 1 because we've already shown the inequality holds for n equals 1. So n naught is at least 2. However, since n naught is the smallest value of n for which the inequality fails, the inequality must hold for n naught minus 1. Well, then part 2 up here tells us that it also holds for n naught, and that's a contradiction. The only way out is that the inequality holds for all values of n, so there's no smallest value for which it fails. In this case, it's pretty routine. For n equals 1, of course, this is just 1 less than 2, which is true. If we assume that this is true for a particular value of n, we need to show then that this is true. When I say a particular value, I mean a fixed value, but we don't know what that value is. It could be any value, but it's fixed. So this is what it all looks like in one line. N less than 2 to the n implies n plus 1 less than 2 to the n plus 1. Well, all we have to do is take this expression and add 1 to both sides, and then do some fiddling with the part on the right. We'll replace 1 by 2 to the n. It preserves the less than sign. And twice 2 to the n is 2 to the n plus 1. Finished. So that's pretty straightforward. This would be referred to as proof by mathematical induction on the variable n, or simply induction on n. Let's try an example that involves sums. Here's a formula. We wish to verify it. This is a formula for the sum of the first n counting numbers. Now, induction is not going to help us find the formula. In this case, n times n plus 1 over 2. But once we, let's say, guess that this might be the formula, induction will prove it is or not. This is what it looks like in summation notation. So induction requires we do two things, that this holds for n equals 1, and that it holds for, if it holds for a value of n, then it holds for the next value, n plus 1. So when we put in n equals 1 in here, we just get this, which is true. The rest is to show that if we assume this, then we can show this. Well, you can see here this same sum that appears above, so we can replace what I've highlighted by this. And that's exactly what I did here. I still have the n plus 1. The rest is algebra, and I will get this. So you can see that the technique of induction applies in situations where we want to prove a whole collection, a whole sequence of propositions, say P of n, that depend on a positive integer n. So P of n in the first case, or first example, was this. In the second example, it was this. But we don't need to start the induction at n equals 1. We can start it anywhere we want, at any integer m, positive or negative. The way to think about induction is, the reason it works is because we know that one proposition is true. In this case, if m is the first index, it would be p of m. Then we show that if any one of the propositions is true, so is the next one. That creates a chain reaction. P of m is true, therefore P of m plus 1 is true. P of m plus 1 is true, therefore P of m plus 2 is true. And we just keep applying that second part, and it shows that all of the propositions must be true. It's a chain reaction. Here's the formal definition, or theorem if you wish. Let m be an integer, that'll be our starting integer, and for all n bigger than or equal to m, let P of n be a proposition that may depend on n. If we can show that the following hold, P of m is true for all n bigger than or equal to m, if P of n is true, then P of n plus 1 is true, then P of n is true for all n bigger than or equal to m. There's some terminology here that's very important. Part 1 here is called the basis step, showing that P of m is true. Part 2 is called the inductive step, and this assumption is called the inductive hypothesis. Hypothesis is a synonym for assumption. Okay. Now, I find that one of the major points of confusion among students is they will think, aren't we really just assuming all of these statements are true? Assuming that P of n is true for all n bigger than or equal to m? No, we're not. What we are doing is showing that if a particular proposition P of n is true, so is the next one, in order to create this chain reaction. That's not the same as just blatantly assuming P of n is true for all n. It may take a little while for that to sink in, but let me give you a somewhat inaccurate analogy. It kind of works. If I said to you, if I go to the bank, then I will get some cash, that does not imply that I am going to the bank. It's a conditional statement, if. It's the same thing with induction. If P of n is true, then so is P of n plus 1. That does not say that P of n is true. Okay. Okay, here's another example using summation for summations. And I'm not going to go through this one. I'll let you do it. It's very similar to the one I did earlier. The algebra is a little more complicated, that's all. Here's an example that does not involve summations. A set of size n has 2 to the n subsets. So in symbols, if the size of S is n, then the size of the power set of S is 2 to the n. And this is really a statement, and I probably should have said that, for n bigger than or equal to 0. Okay. So we can let this be our proposition P of n. P of 0 simply says that if a set has size 0, its power set has size 1. Well, the only set of size 0 is the empty set, and it has precisely one subset, namely itself. So that's true. Suppose now we assume that P of n is true in order, and only in order to show P of n plus 1 is true. So just for concreteness sake, let's say S is this set of size n plus 1. We need to show that it has 2 to the n plus 1 subsets. Well, the first thing to do is to partition the power set of S into 2 blocks. B sub 1 is the block of all subsets of S that do not contain xn plus 1. B2 is the rest of the subsets, the ones that do contain xn plus 1. Well, the reason for doing this is we're trying to use the inductive hypothesis that P of n is true. And that applies directly to B1, because B1 is the set of all subsets of this set, tossed out xn plus 1. And that has size n, and so the inductive hypothesis tells us that, oops, yeah, that's right, B1, the set of all subsets of S that don't contain xn plus 1, has size 2 to the n. What do we do about B2, the subsets that do contain xn plus 1? Well, as it happens, there's a one-to-one correspondence between these 2 blocks. Moving from B1 to B2, all we have to do is toss in the missing element xn plus 1. So a subset, if we take a subset of S that does not contain xn plus 1, and we toss in xn plus 1, we'll get a member of B2 here. And this is a one-to-one correspondence. And I'll leave you to add any explanation you think might be necessary for that. So these 2 blocks have the same size, which means the size of the power set of S is the size of this disjoint union, which is the sum of the 2 sizes, both of which are 2 to the n. And we get 2 to the n plus 1. And that completes the proof by induction on n. Here is one more example of the use of induction, in this case as it relates to De Morgan's laws. This is one of De Morgan's laws. If A and B are subsets of a universal set, a complement of their union is the intersection of their complements. That can be extended to any finite number of subsets of the universal set, and it has the same form. The inductive proof is quite short, and I'm going to skip over it. I suggest you try to do it yourself before you read my proof. It'll be good practice. The version of mathematical induction that we've been discussing here is sometimes called the weak form of induction. And it's because the inductive hypothesis is to assume only P of n in order to prove P of n plus 1. That starts the chain reaction I've been talking about. But we get the same chain reaction if instead of just assuming P of n, we assuming the induction starts at m, we assume P of m through P of n in order to prove P of n plus 1. This is called the strong form of mathematical induction. it gives us more ammunition in the inductive hypothesis. And there are times when that is critically important. Okay. But you can see, I hope, that you get the same effect. Once you have proved that the initial statement P of M is true, you can use this stronger form to get that same chain reaction. So here is the strong form. It looks the same except for the inductive hypothesis. Now you might be thinking, well, if the strong form is stronger, why bother with the weak form? That's a pretty good question, actually. And the cruel answer is you don't need the weak form. But most people will still use the weak form when it is sufficient to do the job. I don't know why that is, but even I do that. If I know the weak form is going to work, I use it. If it turns out it doesn't work, then I say, well, maybe the strong form will work, and I try that. But I'm going to give you some examples where the strong form clearly works, the weak form not so clearly. Ultimately, they're equivalent. So certainly if the weak form works, the strong form will work because you're just adding more assumptions. If the strong form works, the weak form will work, but it may take a lot more effort to make it work. So it's not even worth trying, really. Okay, example. I think you probably know an integer greater than or equal to 2 is prime if it has no positive integral factors other than what it always has to have, 1 in itself. Or put another way, it can't be factored into a product of two integers, both of which are less than p. Okay. I guess I should say positive integers. Okay. One of the fundamental properties of the integers is that any positive integer bigger than or equal to 2 can be factored into a product of prime numbers. One or more. If it's prime already, we consider that a factorization into primes. So again, I'm going to put positive here. Oh, I guess I don't need to because I already have n greater than or equal to 2. Okay. The factorization into primes is unique as well, provided we don't count the order of the factors, which is generally unimportant anyway. This result is called the fundamental theorem of arithmetic. But for this purpose here, we're going to just deal with the existence of factorization and not the uniqueness. In order to prove that any integer bigger than or equal to 2 can be factored into a product of one or more primes, we'll use induction, and we're going to need the strong form. And you'll see why in a minute. So we'll let P of n be that proposition, that any integer greater than or equal to 2 can be factored into primes. P of 2 is true because 2 itself is a prime, and that's, in a sense, a product of primes. Now we get to assume that P of 2 through P of n is true in order to prove that P of n plus 1 is true. Well, if n plus 1 is prime, we don't have anything we have to prove. We're done. If it's not prime, then it must be the product of two smaller positive integers. So say n plus 1 is the product a times b. And A and B both are in the range 2 to n. Well, because A and B are in this range, and because we're using the strong form of induction, we know that P of A and P of B are true. In other words, A is a product of primes and B is a product of primes. And therefore, of course, n plus 1 being AB is a product of primes. And we're done. If we had only assumed the weak, if we're only using the weak form, we would only be allowed to assume that P of n is true in order to prove P of n plus 1. That's not going to work. As a matter of fact, if you look at this factorization, A and B have to be between 2 and n minus 1, really. If A is n, there's no room for B here. N is not a factor of n plus 1 in general. So the weak form totally fails here. At least it's a direct use of the weak form. Okay, let's look at another example. This is kind of a fun one. It's quite common, actually. Suppose that the post office issued only 3-cent and 5-cent stamps. Can we combine these stamps in order to get any amount of postage, positive integral postage, that we want? Well, we can't get 1 cent or 2 cents of postage, obviously. We can get 3 cents, 5 cents. We can't get 4 cents. We can get 6, can't get 7. So it's not clear so far what pattern there might be, but we can get 8-cent postage, 9 cents, and 10 cents. So now it's beginning to look like maybe we can get all postage 8 cents or more. And that sounds like a case for induction. And it will have to be strong induction, as you'll see. The key observation is that if we can construct postage of n minus 2 cents, then by throwing in a 3-cent stamp, we will get n plus 1 cents postage. So if we start the induction at n equals 10 and simply note that P of 8, P of 9, and P of 10 are true, which we saw up here, that will take care of the basis step, which is P of 10. That's true. And the inductive hypothesis will look like this. P of n through P of 10 through P of n are true, where n is at least 10. Can we conclude from this assumption that n minus 2 cents are possible, that P of n minus 2 is true? Well, there's a little wrinkle here. If n is 10, then n minus 2 is 8. But that's why we note that P of 8 is true. If n is 11, n minus 2 is 9, but we've also got that covered. Once n reaches 12, subtracting 2 will still leave it in this range. So it's part of the inductive hypothesis. So we got those two exceptions. N minus 2 falls out of the range from 10 to n. But we've got those two covered. So the inductive hypothesis implies that P of n plus 1 is true. Okay. And therefore P of n is true for all values of n from 10 on, but we also have collected some of the smaller values. So you can get any postage you want except 1, 2, 4, and 7. The principle of mathematical induction is very specialized. but it's kind of amazing how powerful it is and how often it is used. So it's one of the most important proof techniques there is. Related to proof by induction is something called definition by induction. This is very useful somewhat in mathematics, but a lot in computer science. So let's take first a simple example, and that is how we would define the set of non-negative even integers inductively. The set E of non-negative even integers is the set defined by the following conditions. 0 is in E. If n is in E, so is n plus 2. And nothing is in E unless it can be obtained by a finite number of applications of 1 and 2. So what's going on here? Well, the first statement says that 0 is an non-negative even integer. Statement 2 is what creates this chain reaction that we've been talking about. If 0's in E, then you add 2, so 2 is in E, and therefore 4 is in E, and therefore 6 is in E, and so on. The third clause tells us basically that if an integer is not created by the chain reaction, it's not in E. Just because you say what's in E doesn't mean you've said what's not in E, and that's important to understand. If you say something like the elements of E are, and then you've defined it specifically. But if you just say 0's in E and 2's in E and 4's in E and so on, you haven't said what's not in E, and that's the purpose of the third clause. Well, defining the non-negative integers can be done in a variety of ways, many of which are simpler than this, but this illustrates definition by induction. Here's the formal definition of definition by induction. An inductive definition for a set S consists of a basis clause which tells us that certain elements belong to S. It could be more than one element. It could be infinitely many elements. An inductive clause which tells us how to use existing elements of S to get additional elements of S. And a limiting clause which tells us that the only elements that belong to S are the ones we get from a finite number of applications of the basis and inductive clauses. Here's another simple example. We can define the set of binary words also using an inductive definition. So here's our alphabet, the binary alphabet. The basis clause says that the empty word is a binary word. The inductive clause says that if W is a binary word, then so are the words we get by tacking on either a 0 or a 1 to the end of the word. And the limiting clause, nothing is in sigma star binary word unless it can be obtained by a finite number of applications of 1 and 2. Let's take a look at perhaps a more meaningful example of inductive definition. And that is to define what we mean by a well-formed arithmetic expression. Intuitively speaking, an arithmetic expression is an expression formed by adding, subtracting, multiplying, or dividing a finite number of real numbers. We could use complex numbers too. We'll stick to real numbers. Of course, parentheses may be needed in order to avoid ambiguity. So this expression, for example, requires the parentheses to make the result clear. Now, I know there's something called operator precedence, but we're not going to be dealing with that. So we're just starting from the beginning. How do you construct a well-formed arithmetic expression? Also, it never hurts to include additional parentheses. They're not needed, but they do no harm. And that will help us in the definition. So you might want to think a bit about this a minute before we look at the inductive definition. How would you define what it means to be a well-formed arithmetic expression? And here's the inductive definition. The set S of all well-formed arithmetic expressions over the reals is defined as follows. This is the basis clause. Every real number is a well-formed arithmetic expression. The inductive clause, if x and y are well-formed arithmetic expressions, then so are all of these. Positive x with the parentheses around them, negative x, x plus y, x minus y, x times y, x divided by y, provided y is not 0, and the limiting clause. Okay, we have one more short matter to discuss, and we will be done with this chapter, and that is proof by contradiction. I hope I've impressed upon you by now the fact that proofs are extremely important in mathematics. There's no magic formula for finding proofs. There's no quadratic equation. There's no algorithm. Every theorem requires its own proof. And there are techniques, of course, like induction. But the only way to become proficient at doing proofs is to practice, practice, practice. I do want to discuss one additional proof technique, and that is proof by contradiction. Very simple idea. We assume that the result we're trying to prove is false, and then try to deduce a contradiction. And the only way out of that contradiction is that the result was in fact true. Let me show you a couple of simple examples. Here is a theorem: the product of any two rational numbers is rational. And another theorem: the product of any non-zero rational number and any irrational number is irrational. I'm going to prove the first theorem by giving what would be called a direct proof, not a proof by contradiction. I'll prove the second theorem using the technique of proof by contradiction. So for the first proof, product of any two rational numbers is rational. Let R1 and R2 be rational numbers. Then, according to the definition of rational number, there are integers for which R1 is P1 over Q1, Q1 not 0, R2 is P2 over Q2, Q2 not 0. Then the product is R1, R2, which can be simplified to this. And since Q1 times Q2 is non-zero, the numerator and denominator are integers. The product R1, R2 is rational. So we started with two rational numbers. We took their product and showed that that was also rational. That's a direct proof. Let's try a proof now by contradiction. The product of any non-zero rational number and any irrational number is irrational. So we assume that that is not true. That means there's a non-zero rational number r and an irrational number x for which the product Rx is rational. And we want to find a contradiction. Well, since the product is rational, there are integers p and q, q not 0, for which Rx equals p over q. But r is rational, and so it has the form, say, m over n. We make that substitution here. M over nx equals p over q. Solve for x. Q times m is non-zero. Lo and behold, x is rational, but it's not rational, it's irrational. Contradiction. And the fault can only lie in our assumption that the result we're trying to prove is false. Therefore, it must be true. Let's look at one more. We proved the following result using induction, that n is less than 2 to the n for all positive integers n. Let's try a proof by contradiction. If we assume that this is false, there must be a smallest positive integer k for which it is false, and in other words, for which 2 to the k is less than or equal to k. K is bigger than or equal to 2. For k equals 1, that's not the case. So k minus 1 is also positive, and since it's less than k, this inequality holds for k minus 1. For n equals k minus 1, that gives us this. Now a little algebra, multiply both sides by 2, combine it with this, and we end up with this. Add 2 to both sides, subtract k, we get k less than 2, which is false. So our initial assumption is wrong, and this inequality holds for all positive integers n. So that is a proof by contradiction. Okay, we have finished chapter 1 at long last. I hope there were some features in it that interested you, and I thank you for watching, and I hope to see you in chapter 2.